This was intended to be for the students, so I wanted something that was approachable for them. I decided to choose a simple shortest path problem, which you wouldn't think shortest path problems have any new results. I have a surprise for you. This idea came to me last summer as I was riding my horse in the Cascades, where I spend my summers. And my horse and I rode out about 10 miles, and we had some trouble on the trails, and so we decided to take a different trail back to where we started from. And he's a very well-trained trail horse, so at every junction, even though we're in a ponderosa forest, at every junction he'll try to go back the same way we came. And I had to correct him. But I realized, his intuition 80% of the time was right. Then I got to thinking about shortest path problems. Then I got to thinking about, wait a minute, there's something new here. So I want to walk you through this something new, and it's pretty approachable, I think. So the shortest path problem is one of the simplest problems in operations research. It was studied by Leonard Euler, of all things. The first algorithms were published in the early 50s by Dijkstra. This was the first time it became fashionable to actually talk about a computer procedure as well as a proof of correctness and an argument for how much data space was required. It's a very, very ubiquitous problem, well studied, so how could you possibly improve it? There are a couple of standard algorithms. One is called Floyd-Warshall. Every little student learns it. It's seven statements long, frustrating as heck, because you never discover the optimal solution until the last step. So it always takes the maximum amount of time to get the minimal answer. The one thing about Floyd-Warshall that's frustrating is when you look at it operate, you can see paths begin to appear. At the first iteration, you get all the one-hop paths. At the second iteration, you get the two-hop paths, and so forth. But you don't discover the true solution until you do the nth operation for the n-hop paths. The other thing we do is repeated shortest path methods by other means. And these are the really fast methods of which we usually choose some subset to teach our students. So they're very well known, well understood. If you take a networks class, you'll study those with us. There's this Bellman-Dijkstra algorithm. There's lots and lots of other ones. Some of them work on specialized graphs, acyclic graphs, sparse graphs, and so forth. Our world is typically sparse graphs. If you look at road networks, for instance, they have about degree 2. If you look at C-route networks, they have degree about 2. If you look at promotion networks, they have a degree about 2, keep or go. There are some applications that are very dense. Most of them are fairly sparse. This is sort of a laundry list of applications. There's a color code here. The undergraduates wouldn't know this, but the graduate students would. One of the things we develop as a characterization of an algorithm is the worst case runtime, the longest runtime. The ones in black over there have a worst case runtime that's polynomial, which we generally think that's a good thing. It means that the worst case runtime is just a function of the number of nodes and the number of arcs, but not the data. The red one there is a worst case runtime, which is a function of data, which we call pseudo-polynomial. That's typically bad news because it means that the magnitude of the distances, the magnitude of the cost, the magnitude of the transitions determine how long the algorithm might run worst case. The remarkable counterintuitive thing about this is that the best algorithms and the fastest algorithms are the ones in red, the ones with the worst bound. Okay? We look for general purpose algorithms. Tomorrow for the students, I will show a blue water application of this that's now being used in 3rd and 7th and 5th fleets. And as we were working on this application under the hood, I suddenly realized, oh, I need some C routes here. I need C routes from all possible sources to all possible destinations of all my supply ships worldwide. And found out that hadn't been solved before, or hadn't been solved well. It took too long. That's what set us loose on this side path here. Okay, the basics for a label correcting algorithm, this was intended for the undergraduates again, is if we're going from one node S to all other nodes, is from that distinguished node S we create a label. How far is it from S to itself? 0. We then try to discover how far is it from S to all other nodes. And we do this by some sort of trial and error. And eventually we'll find other nodes that are close to S, and we'll label those. And then we may discover those labels can be improved, and we'll improve those. And we'll continue by some systematic means until we're sure that all the labels are the correct labels. Well, the difference between a one-to-all shortest path method and an all-to-all shortest path method is typically just do one-to-all for all nodes. Just for node 1, do one-to-all, node 2, do one-to-all, and so forth, which seems kind of stupid. Turns out that's the ideal thing to do. So when we do this, we say, let's add S to a list of interesting nodes. These are the ones that we are kind of focusing on, like close to home. And while that list is non-empty, pull a node off the list, and find all its immediate neighbors. When you find its immediate neighbors, you say, how far is it to S? How far is it to my immediate neighbor? Ooh, is that closer than before? Let's improve that label, throw it back in the list. Is it not closer than before? All right, let's continue. Pretty simple. Okay? What happens as a result of the output of these methods is you get a thing that's called a tree of shortest paths. Again, I'm getting a little technical here, but this is right at the edge of what the undergraduates would have seen. What we have here is all the distance labels of the shortest paths from S to all other nodes. So the distance label for node I out there is how far I found it is to go from, say, Annapolis to Monterey. And that's about the longest distance label there is, by the way, in the country. I'm here to tell you. And then I find out if I was in Monterey, what's the first city I would have come from to get from Annapolis. So that's what those predecessors are. So that gives us the means of walking our way back across the country through the shortest path we've discovered to get from Annapolis to Monterey. But there's more. Okay, this is where the theoretical thing came in. Now, when you ride a horse, I'm here to tell you, you got to think through the horse's head and the horse's mind. I have a hot horse. If I don't pay attention to him, he'll bend me up. He'll hurt me. I got to think like he does all the time. But I had a couple of side cycles as we're thinking about this, and I thought, you know, the principle of optimality really applies all the time for every one of these solutions. Okay, let's apply this principle of optimality and stop throwing away results that we have in hand but we're not paying attention to. So these algorithms all differ in how they handle things, but basically among all of these, probably the best known is the DQ, which is the one with the worst bound, but it's very, very fast. And the least known, which we've now resurrected, is a thing called 2Q, which goes back about 20 years, but it's just not taught. The idea of 2Q is to keep two pools of nodes, the nodes you're interested in and the nodes that can wait. Okay? Bellman itself, I'll get back to it. Bellman itself is great in theory, has a polynomial bound, mediocre in practice. DQ is terrible in theory, has a terrible pseudo-polynomial bound, but very competitive in practice. Threshold algorithm is good, except it requires a lot of tuning, a lot of ad hocery, which makes me nervous. The 2Q is obscure. It has a good bound, and it's good in practice. So what we're doing is trying to resurrect this and convince people that it's good. We found in benchmarks that's the fastest algorithm we had. So let's start with that one and see if we can make it faster. So the way 2Q works is to keep what's called a DQ, a ring. And what we've got is one component, which is the interesting nodes that we're really working on hard, and the other component, which is the nodes we've thrown away for now. We'll get to them later as we proceed. So it's a pretty simple idea. If a node looks good and gets improved, put it in the hot list. If it looks good and is not improved, throw it in the cold list. What could be easier? By the way, the pseudocode for this is available from a paper I can give you. It's less than 1 page. It's about 18 instructions. It's very primitive code. Okay, so I've already talked about this cleanup and the sweeping algorithm. You guys are more experienced than the undergraduates. This is a review you don't need. Another approach to this is to look at what happens as you get partial results. Well, it turns out that Floyd Warshall is 7 instructions long, really lousy performance, and you don't see the answer until the very end. Repeated shortest path works pretty well and it's intuitive, but it takes a lot of patience. You can't predict how long it will take, and there are instances that people have come up with that are perverse and take the maximum amount of time. Okay, so every time we solve a one-to-all shortest path problem, we get a result that's what's called the shortest path search tree. And this shortest path search tree has more information in it than has been typically used. Let me show you what I mean. Here's a shortest path search tree from node K, where K is 1, 2, 3, 4, 5, to all other nodes. What we use this for classically is to know what the shortest paths are from all other nodes back to K. But by the principle of optimality, what we've discovered and never before used, throughout our literature at least, is that at every other shortest path in the shortest path tree is also a shortest path. That's the principle of optimality. But wait, if I already know the shortest path from I to J, and I have not yet processed node J, why would I throw this away until I process node J? Why wouldn't I take advantage of this knowledge and extract from the shortest path tree this shortest path and store it for future use when I finally get to node J? Because as it turns out, if you have an advanced idea of how far a node is from your source node, it makes things go faster. I'm not sure when I get to node J if this will be the shortest path from J to all the nodes, but I know this is a very interesting path. This is the path my horse was trying to take to get me back to where we started, to get me back to my trailer. So a very simple idea is, for every node that we solve, one to many, find the shortest path tree and go through and extract from the shortest path tree every shortest path that's revealed in there. Actually traverse the entire tree and record all those shortest paths that you find that have not yet been processed so that you can exploit them in the future. Simple idea. Okay, for all shortest paths, we just do the shortest path method from S to all again and again and again. Just requires rhythm, as before. But now we've added a new pre-process. The pre-process says if any node has a finite distance label to node K, because we've seen it before, put it on the queue. That's new. Okay? Then we'll solve the shortest path tree, but with this prior information, which is my horse remembering a lot of really good turns, trying to get back to my trailer, solve the shortest path tree. At the end, before we throw these results away, record all the shortest paths for future use. Okay? Really simple idea. Okay. So we've generated lots of random problems. We've also looked at road networks. We looked at Delmarva. We looked at California. We've looked at sea route networks. We've looked at air route networks. For those of you brown shoes, air route networks come into play because we have winds aloft, which means that getting from I to J is not quite the same as getting from J to I. In sea routes, we have set and drift. We have submarine networks, same story. Well, that got me to thinking, well, wait a minute. If this works for a symmetric network, might it work for a near symmetric network? If I know from I to J is pretty short going in one direction, how about from J to I? Well, wait a minute, that distance is a valid label. Okay, I can actually precede with that label and maybe improve it, but I will then encounter that label later with prior knowledge. So we implemented this. Here's some of the results. This is number of seconds of runtime. This is number of nodes. By the time you get out here, you're finding that number of squared paths. That's a lot of shortest paths that you're finding for all shortest paths. As I mentioned, this is a lightning-fast class of algorithms. So what we see here is classic methods like Floyd-Warshall, which is immediately explosively slow. Classic methods like the 2Q, which is obscure, but we think is worth re-looking at again, and we rewrite textbooks to start using it. This is Dijkstra's method, which is the 1956 method, which is easy. It's competitive for a while. And this is the 2Q method with update, which is uniformly faster everywhere. Big surprise, my horse was right. Okay. So here we have a runtime versus node degree. So here's very sparse nodes, degree 10 nodes. Every node has 10 neighbors, 20 neighbors, 30 neighbors, all the way up to full dense. You only see problems like this occasionally in physics and electro-optics and crystallography, but they do occur. Again, you see Floyd-Warshall gets really bad really fast, and then essentially it's just running in constant time because it's as slow as it can be. And again, by golly, this 2Q is faster for all but the most dense problems. And if you add this update, this simple idea my horse had, it's even faster than that. Okay, now we introduce skew. Skew is a degree of asymmetry. So skew of 0 means I'm completely symmetric. A skew of 0.2 means if it's from I to J, this takes distance d, then J to I may take distance d plus or minus 20%, and plus or minus 40%, all the way up to plus or minus 100%. Here we have performance of 2Q and 2Q with a new update. So even with very, very highly skewed asymmetric networks, this idea that my horse had is really fast. So our conclusions are, it's almost time for lunch. Our conclusions are, we've discovered something that seems to dominate everything in the literature. It's a surprise for you guys. Never give up on classic methods. They can all be improved. There's a lot of results left out there. This is not scorched earth. Even your horse can give you an idea like this. And thank you.